Yes, so let me, so I'll have some slides, but I'll start just from the document camera. So I hope you can see that. And so.
Okay, go ahead, Yuval.
Okay, so the first part of the talk will be on high-dimensional matchings and how we can analyze them via a tree approximation of Euclidean space. Now, as you all know, approximating high-dimensional space by a tree or Bethe lattice is a classical device in physics. Here, we're not going to look at lattice process, but rather a high-dimensional point process just obtained from taking uniform points. So we go to the next page and just so if you take a large box of volume n and throw in n uniform points in the box, and now you take a limit as the volume of the box goes to infinity, you'll get a process in the whole of Euclidean space, which is the classical Poisson point process. So if you like to think of it in the Poisson terms, that's great, or you can just think of a limit of a uniform cloud of particles in a box where we have 1 point per unit volume. So that's our basic process. And we're looking at we want to understand the local geometry of this in very high dimensions, and what is the real tree structure that approximates it well. And then we'll apply this to some matching, multicolor matching problems. So the key, we want to understand the local geometry. So let's start at 1 point and ask, where is the closest point? So the distance to the closest point, we can write down its distribution, but it's better to look at the volume to the closest point. So if this is the origin where we started, then we look at the closest point to the origin. It's in some distance r away. What we can say is, if we look at the volume of the ball until we reach this first point, so what is this volume? Of course, if the radius r, it's omega d r to the d, where omega d is just the volume of the d-dimensional unit ball. Now, how is this volume distributed? Well, it exactly is an exponential random variable. So just like we have in the standard one-dimensional Poisson process, if we start from 0 and we have point process on the line, and I'm sorry, the camera, I have to tune the camera so this is visible, right? Then the distance from 0 to the first point in the Poisson process has an exponential, standard exponential distribution, and then the next distance is also exponential. So the same thing happens in Euclidean space for volumes, because the chance that a ball of radius r is empty is exactly e to the minus its volume. So this is easy. And then if we look at what is the whole sequence of points in increasing distance from the origin, then if we record not the distances to these points, but the volumes of the balls to these points, we will exactly get a one-dimensional Poisson process. So the distances will just, these volumes are just behaving exponentially. So then the question is,
Yuval, you're taking the density to be 1, the average density.
Yes, I'm now taking the density to be 1. Thank you, Joel. Yeah. So then, well, so this is just from the perspective of 1 point. So by looking at the sequence of volumes, we're getting this one-dimensional Poisson process. But what is where is the tree coming? It's when we look. So let's look at the closest point, and now we're going to draw the same picture from perspective of this point. So if this was the origin, this was the point x1 that was the closest one. Now we're going to draw the same picture from the perspective of this point. And here is where the two-dimensional visual is so lacking when describing the high-dimensional picture. So what happens, I'll just start over here, So we have origin and we have this point x1. Okay, now we do the same picture from the point of view of x1. So we look at the first point closest to x1, and we can call this x11. So this closest point, of course, the volume from x1 to this closest point will also have this exponential distribution, and we're looking at the closest point excluding the origin. So we're ignoring the origin now, we're looking at the closest point. Now, in low-dimensional space, this, when we look at the closest point to x1, it will be a candidate also to be close to 0. But in high-dimensional space, that's not the case at all. So if we look at the distance to x1 and then the distance to, so when we start from the origin and look at the first point, and then we look at the next point and the next, these are very clustered together in terms of distance because, so there's a lot of concentration because of this mapping between distance and volume. So the distance to the first point is going to be, right? We know that this volume has exponential distribution, but if we go to the next point after that, the ratio of the distances will be 1 plus little o of 1 because volume grows so fast as we increase the radius. So if we record the points closer to the origin, their distances are all clustered together. But if we look at x1 and the next closest point, the first closest point to that, what I marked as x11 here, these vectors are actually going to be orthogonal in high-dimensional space. So when I go to x1 and then go to x11, the closest point to that, ignoring the origin, the distance will grow by a factor of √2, which means x11 is not at all in the running to be one of the closest points to the origin. And that's where the underlying tree structure is. So it turns out if I want to describe the local geometry of this cloud of particles, the right structure, and I'll show you its application to actually proving some theorems, but the right structure to approximate is a structure which was invented by Aldous and Steel, which they call the PWIT. So this is the Poisson-weighted, Poisson-weighted infinite tree, and this is the underlying tree structure. So we start at the root, and the root has infinitely many children, but only for any question we ask, only finitely many of these will be relevant. And these children have separate, so the edges connecting to the children have lengths, and these lengths form this Poisson process. So this is the first length, L1, this is the second length, L2, and so on. And these lengths are just coming when we start from the origin and write a Poisson process. So this is a Poisson process in one dimension. So L1 is the first length, L2 is just the distance from the origin to the second point, L3 is the distance to the third point, and so on. And so we take these distances in the one-dimensional process and create a tree based on these distances where the connection to each point is a separate edge. So the lengths of these edges, or you could also call them weights, are just the distances taken from the one-dimensional Poisson process. So this is layer 1 of the tree, and because this Poisson process on the line is infinite, there are infinitely many children here, but most of them, as we'll see for the questions we study, will be irrelevant. Now, we take every vertex here, and we repeat the same story from this vertex. So this vertex at distance L1 from the origin, it was x1, it has itself children at increasing distances, so L11, L12, and so on. And these increasing distances, again, form an independent Poisson process. So we create a new Poisson process corresponding to this vertex x1, and the distances from the origin to the points of this process we mark on this tree. And we do the same for every vertex here. Okay, so we have a branching structure which just continues this way. Every node has infinitely many children, And the distance.
Can you go from L1 to L2 points?
So there is no, this is a tree, so there's no connection between, this point x1 and the point x2.
Oh, so you don't look at the point at the first.
From the origin, it has infinitely many children at distances, and this is going to be a tree, so there are no loops. From the origin, we have x1, x2, x3, and so on at distances L1, L2, L3, and so on, which are the distances from this Poisson process. So they're the distances from the origin to all the points in this Poisson process. Okay, so that's how we create the first level of the tree. The first level already has infinitely many vertices. Now to continue, we just continue in a self-similar manner, the same way from each of these points. So if you take x1, what is the structure to the right of x1? It just has a sequence of edges, the first of length L11, the second of length L12, and so on. And these come from a new Poisson process on the line. So this would be L11, and then this second point here will be a distance L12 from the origin, and so on.
Sorry, Yuval, I'm just trying to understand. When you go from x1, can you hit x2?
No, absolutely not. So it's a tree, and all the descendants of x1 are disjoint from all the descendants of x2. You never hit x2. So again, it's a tree structure. So what happens to the right of x1 and what happens to the right of x2 are disjoint and independent.
Okay, thank you.
Okay, so when you do the Poisson process in Euclidean space, and as I described it before, you don't have this perfect independence. However, this ideal tree structure is the correct description of the limit of these, the local geometry of the Poisson process in Euclidean space when we let the dimension tend to infinity. And it turns out to have real implications for finite high dimensions, and I will show you one in the rest of the talk. So this is kind of the introduction to the PWIT, and we'll see it appear in action soon. And the kind of problem we're going to apply it to is the problem of greedy or stable matching. So I'll show you more about that in the slides, but so suppose we have points, and they could have some restrictions, but first just think of points in space, and we want to create a matching. So one way to do that, if we have a finite collection, what would be greedy matching? It's easy. Take the two closest points, match them, remove them, and repeat. And that would be greedy matching, and would conclude in finitely many steps if we just have n points. But if we have an infinite cloud, what is the analog of greedy matching in an infinite cloud? So we can't take the two closest points because the distances are arbitrarily small. But what we could do, each point can select the closest point to it, because locally, for every point locally, the other, there is a closest point. So there just isn't a closest pair when we look globally. But if I look from one point here, I can find the closest point and select it. And this point can find a closest point and select that, and so on. And however, sometimes and often we'll have 2 points that select each other. So we have x and y, where y is closest to x and x is closest to y. When we have such a pair, we're going to match them up and remove them from the matching marketplace. So when we look at the whole infinite structure, there will be positive density of such pairs. There will be many pairs which prefer each other, where the preference is according to distance. These pairs get matched and removed from the game, so others can no longer select them. And after they get matched, we can repeat, and for each point, select again the closest available other point. And when we have a pair that select each other, we remove them. And when we iterate this process, if we have no restrictions on who can match with whom, we will get a perfect matching of all the points in the limit. Now, this description is quite simple and direct, and it gives you algorithm you can implement in finite volume. It's a special case of a more general problem, which works with more general preference orders, which is the stable matching problem. I'll say about that in a moment, but in more detail. But let me just say now, if we have a matching, we can describe an unstable pair as a pair of points that prefer each other to their matches. So suppose, let me show this in the picture. Suppose I have a picture like this. So here are 4 points, and if we look at these two, they are closer to each other than to their matched pairs. So the matched pairs are indicated by these edges. So we would refer to this pair as if we have a matching that looks like this would never arise from the greedy procedure I described. But if we would have a pair like this, we would call them an unstable pair. An unstable pair means an unmatched pair that prefer each other according to distance compared to their matches. And there is a general theory actually created by Gale and Shapley, or initiated by them in 1962, of stable matching. So it turns out that for any preference ordering of when you have in the bipartite case, there is a stable matching. Here we're in a simpler situation where the preference ordering is by distance, and the key is it's symmetric. So everyone is employing the same metric for the preference ordering. And in that case, the stable matching exists and is unique and is given by this greedy procedure. It's very easy to check that when you apply this greedy procedure iteratively, there will be no unstable pairs. Because if there is such a pair, you look at the member of the pair that was matched earlier, and you see this cannot be, because because of the greedy procedure really ensures there can be no such unstable pairs. So I will now switch to the slides and talk for a while about we know unstable matching according to distance, which is the same as the greedy matching, and then come to the application of this Poisson-weighted infinite tree to give some insight into a problem which is still very much open. So I will switch now. Let me see. I have to before I switch, I have to open the PDF. Okay. So now I want for a while to focus on how we use the Poisson-weighted infinite tree, the PWIT, for analyzing some greedy or stable matchings. Let me see if I can. I think this is already quite big. Okay, so as I told you, a pair XY is unstable if X prefers Y to its match and Y prefers X to its match. And if there are no unstable pairs, we get a stable matching. And when the preference is according to distance, the unique stable matching is given by this greedy procedure. Now, actually, in the work of Gale and Shapley, they focused on the bipartite stable matching, where so we can think of the points have 2 colors, blue and red, and we only allow edges between blue and red nodes, but the rules are still the same. So when we talk about unstable pairs, they have to be a blue and red pair, and when we do the greedy matching procedure, every blue point selects the closest red point, every red point selects the closest blue point. If a blue and red select each other, they are matched, and we repeat. Okay, and here is a picture of the bipartite stable matching of 1,000 red and 1,000 blue points. And so stability is a nice criterion, but it's very different from global optimality. So if you took these 1,000, by the way, the points I didn't say, it's on a torus, so we have periodic boundary conditions in this picture. So points connect across these boundaries. But if we were to take the optimal matching, means the one with a minimal total sum or minimal average sum, then there would be no edges crossing. That's very easy to prove. But in the stable matching, we do have many edges that cross each other. The stable or greedy matching, is very far from optimal in some kind of global way, but it is natural to arise when, if you think of the points are agents that optimize for themselves. If a blue and red point are very close, they will just want to match to each other rather than worry about global optimality. And see here, so I switched from the second picture has the same collection of points, but now this is the minimal length matching. So the total length is smaller, but in this picture you do have definitely some, even many unstable pairs. So okay, so I will continue with that, and in the bipartite case, for general preference orderings, the Gale-Shapley algorithm will find a stable matching, but the stable matching is not unique in that general setting. I will kind of skip this discussion of the Gale-Shapley algorithm. It's not directly relevant for what we're doing here. And if the preference functions are symmetric, which is true in our case, so just go to the bottom here. If the preference function is based on distance, then the stable matching is unique, and it's given by the greedy procedure, as I mentioned. Okay, so here's the picture for the one color matching, and this is a stable matching of 2,000 points, uniformly distributed in a torus, and as I said, can be built in the greedy way. And this one we understand very well. And in fact, there is a paper on this topic that I wrote it's already 14 years ago, with Ander Holroyd, Robin P. Mantel, and Oded Schramm. It was one of Oded's last papers. And we look there at the distance that points are matched. In that case, it's very easy to see all points are matched. But if we take a typical point and look at what is the distance from X to its matched pair, then what is the distribution of that distance for a typical point? So it basically has a finite Bethe moments if you're in RD, but no better moments. So I'm sorry, I said it exactly the opposite. So it has an infinite Bethe moment, but all moments that are less than D are finite. That's the second statement here that says the tails are at most R to the minus D. So this means that if you take any moment that is less than D, then it will be finite. So we have a good understanding of the matching distance in the one type matching problem. So that is the topic of another talk. I won't go into these proofs. Let me say that in the bipartite case, again, we have blue and red points. We still know it's very easy to show that if the blue and red points have the same density, then they're all matched. While if the density of one color is, so if the density of red is P, which is less than half, then all red points are matched, and there's a positive density of blue points that are left unmatched. That's very natural and easy to prove. If you have P equals a half equal blue and red points, then the stable matching is perfect. All points are matched. And only in dimension 1 we understand the distribution of the matching distance. So that is one open problem to understand how many moments does the matching distance have in bipartite matching in higher dimensions? But I'm not going into that right now. And the problem, what is easy to prove is that the matching is perfect. All points get matched. Now I come to the example where we will use the PWIT, which is the two-type asymmetric stable matching. So we start with a uniform cloud of particles, S, this Poisson process of rate 1 in all of space, RD. And each point independently color red with probability epsilon, blue with probability 1 minus epsilon. But now the matching rule is asymmetric. Blues can match with blues and with reds, but reds will not match with other reds. So we're putting the red density at epsilon on purpose. So we think of the red density as small. Okay. So if epsilon was large, then of course there will be blue points left over. And it's easy to see that if it's also true for epsilon, which is less than half but close to a half, because some blue points will be matched to red points. So again, if epsilon is small, so because blues are matching with reds and blues are matching with blues, but reds cannot match with reds, there is some asymmetry. So we expect some blue points to be left over, and see, so we expect here some red points to be left over, and because if it was all just bipartite, blue and red, then the density is a half, it's clear. But here, because some blue, from the perspective of the reds, some blues are lost to matching with other blues, then there will be reds that will tend to be left over. And the question is, which is open, is that still true if the density of reds is very low, epsilon? And this is open for all d bigger than 1. So again, the problem is you start with epsilon density of reds and think of epsilon as small. And now you apply this greedy matching with these asymmetric matching rules. Are there always red points left over? Or if epsilon is small enough, all the red points will be matched? We don't know the answer to this in any fixed dimension, RD. So what can we, but we can answer this in a different form if you fix epsilon and then make dimension high. This is a picture of the asymmetric two-type model, 1,000 red points, 5,000 blue points. So epsilon here is 1/6. So we apply this greedy matching procedure. So again, every point selects the closest point that it can legally be matched to. Reds will select only blues. Blues can select blues and reds. And if 2 points select each other, they are matched. Otherwise, they are, those that are closest, that select each other are matched, they are removed, and then the process is iterated. So the question is, in the end, are there red points left over? And note that there can be no blue points left over, because if there are many blue points left over, they will just match to each other. So the only question is, are there red points left over, the ones who are more picky and won't match to their own kind? So in this picture, the leftover red points at the end of the process are recolored by green so we can see them. If you look closely, there are various green points. They tend to cluster a bit. And so the open question is, do these points red points left over exist no matter how low the density is. And if you fix the dimension and let epsilon be small, we don't know the answer and it's open. So what can we prove? We can prove a version where we first fix epsilon, then we look at this model, and then we make the dimension high. So for any fixed epsilon, if the dimension is high enough, and high is really high here, it's about e to the 1 over epsilon, then we can show that there, even though the initial density of red points is very low, this epsilon, then there are still unmatched red points at the end with probability 1. And we can even say what is the asymptotic density of the unmatched red point. So it's a tiny fraction of, so we started with epsilon red points, and the unmatched ones in the limit will be a much tinier fraction of that. So you see this epsilon e to the minus 1 over epsilon. So we have an exact value for the limit. And so in some sense, we understand this problem with fixed epsilon and dimension going to infinity. In another sense, we don't understand it, because if you fix d and then let epsilon tend to 0 and ask, is there some tiny positive epsilon where all the red points are matched? We cannot answer that question, even in dimension 1. This is particularly embarrassing. There's a multi-type version, which I'll skip. And now I want to tell you, so this precise result in high dimension, so how do we prove it? We prove it by carefully, rigorously relating the problem to the problem in the PWIT that I told you about before, again, invented by Aldous and Steel in 2004. And this is another picture of how it looks. Again, from a point, we have these distances to the children, which are a Poisson process, and from each of these children we have its own copy of this, and so on. And this is the tree that we will use. Okay, so this is what I described earlier, and it was invented by Aldous and Steel to describe the limit of processes in mean fields, so on the complete graph. And I won't go into their application. They were not thinking of high-dimensional Euclidean space, but the tool they created turns out to be perfect for our problem, and in general, to understand the local geometry of a high-dimensional Poisson process. So here I'm repeating what I told you before with the, and on paper, that, but it's worth repeating because this is the foundation of what we're doing here. So we consider a Poisson process of rate 1 in Euclidean space, seen from a typical point, which we can think of as the origin. And then x1, x2, x3 are the other points of the process written in order of their distance from the origin. Then the sequence of volumes, omega d xi to the d, of the sequence of volumes from the origin to the points ordered according to distance. This is just a standard Poisson process of rate 1 on the positive reals, and the distance to the first point will be asymptotically concentrated in this value, the volume of the unit ball to the power of minus 1 over d. So as d goes to infinity, we will definitely find the first point within 1 plus little o of 1 of this distance. And the second point and the third point and the fourth point will all be very close to this distance. But if we look at the points closest to x1, ignoring the origin, then these points we can write as x11, x12, and so on. Now we're still in Euclidean space, but when we scale them similarly, so look at the volumes corresponding to the distance from x1 to x11, then we have convergence to a Poisson process, and we expect and can prove that the vector from the origin to x1 and the vector from x1 to x11 are approximately orthogonal. So this is just the fact that on a high-dimensional sphere, most of the volume is concentrated near the equator. So if you fix a vector like the vector connecting from the origin to the North Pole, or any vector, then most other vectors on the sphere are orthogonal to, or almost orthogonal to, that vector because of this Paul-Lévy observation on the concentration of mass near the equator. So this means that the x11 is at distance about √2 times this number, omega d to the minus 1 over d, from the origin. So it's not at all, x11 is not at all in the list of the first 10 or the first 1,000 points from the point of view of the origin. Okay, so that's why this tree structure really, and this is some formal statement saying that because of this observation, we can solve problems on local geometry in Euclidean space by coupling it to the same problem on this PWIT. So as long as we remember to rescale that distances on the PWIT correspond to volumes in Euclidean space, then we can really solve the limiting problem as d grows by solving it on the PWIT. So in order to understand stable matching in Euclidean space, we can understand stable matching on the PWIT, provided we're willing to work in high enough dimension. So, so let's look at first one color matching, just kind of a warm-up. So that's the simplest matching problem on the PWIT. So, so again, the PWIT has this recursive structure, and we'll say that if j is a child of the root along an edge with weight or length tj, we say that j is available to the root if j is not matched along an edge with weight less than tj in the subtree rooted at j. So, so when we look from the point of view of the root, it looks with which of its children can it be matched? And the answer is, well, with the first child that's not better matched inside its subtree. So if j is a child of the root, to ask if the root is matched to j, we look at the distance from the root to j. This is some distance tj, and well, is j even available to the root with this distance? The answer is no if j is matched better within its subtree, and yes if it's matching within its subtree is worse than its distance to the origin. So that's the key comparison. So before deciding who we match to the root, we look from the root to each of these candidates and ask, is the candidate even available? So if a candidate is at distance 100, but within its subtree it's matched within distance 80, it's not available. But if it's a distance 100 and the best matching within its subtree is 110, then it's available to the origin. And then the origin will be matched to the first available child. That's what we get on the PWIT. So this, and then we can use the recursive structure. It's a version of, really a very simplified version of the cavity method that will allow us to solve the problem on the PWIT. So, so let's get a little more quantitative. So if x of t is the probability that the root, so now we're doing this warm-up problem, which was all we will calculate because I don't want to do you know, technical calculations. But if x of t is the probability that the root is not matched along an edge of length less than t, then the weights from the, then, you know, we look at the weights from the root to its children, and each of these children we ask, is it available to the root? So remember, that means that it's it is not matched within its subtree better than its distance to the root. So so the probability that the root is available to the origin, sorry, let me say it again. Probability that the first child, 1, is available to the origin, if their distance is t1, this probability is exactly x of t1. Because, so remember, x of t is the probability that the root is not matched along an edge less than t, but the same thing applies to the vertex 1. So if we look at the vertex 1 within its subtree, what's the chance that it's not matched within it? What's the chance that it's not matched within its subtree? It's going to be, sorry, I have to close something. So, so this chance is exactly x of t1. That's a chance that no one in its subtree is matched to it at a distance closer than the distance to the root. If that happens, it's available to the root. So so the children are available independently with probabilities x of t1, x of t2. So the process of available children of the root, if we now put it on one line, it's now an inhomogeneous Poisson process with a rate function instead of rate 1, it has a rate function x of t. So, and the root is matched to the first point of this process. So if we ask what is the chance the root is not within this match within distance t, this is, on the one hand, this is what we define to be x of t. On the other hand, it's the probability that the inhomogeneous Poisson process with rate function x will have no points in an interval from 0 to t. Now, a classical property of Poisson process is if we want to know if some set is empty for a Poisson process, the probability of that is e to the minus the expected number of points in that set. So if we have from 0 to t, the expected number of points for this inhomogeneous Poisson process is this integral, and exponential of minus that gives us the probability that there are no points. But by definition, this is exactly x of t. So we have this identity for the function x of t, which allows us to solve for x of t. So this is a warm-up kind of Bayes' problem. Once we understand this recursive structure gives us this equation, we differentiate, we get this very basic differential equation, which together with the boundary condition x of 0 is 1, because the probability we're matched within a tiny distance is 0, so probability we remain unmatched is 1. So x of 0 is 1. And with this differential equation, the only solution is 1 over t plus 1. So because x of t is going to 0, the consequence is that as t goes to infinity, the root is matched with probability 1 if we don't restrict the distance. But this tells us that the chance it's restricted, it's mapped within distance t is asymptotic to, the chance that it's unmatched within distance t is asymptotic to 1 over t. Now, because t here in the PWIT corresponds to r to the d in Euclidean space, this matches the result that we already proved in the earlier work with Pimentel, Schramm, Holroyd, that in Euclidean space for the one-type matching, the distribution of the distance to the matched point has a critical Dth moment. So the probability, the tails are r to the minus d. So the tails r to the minus d in Euclidean space, which in that case are proved for all dimensions, they correspond to the tails 1 over t, or 1 over t plus 1, that doesn't matter, that we find in the PWIT. So this case is just reproving in an asymptotic form for high dimension a result that we already know for all dimensions. But that's because one-type matching is a very easy problem. Now, when we go to the asymmetric two-type matching, so I'll just describe, the differential equation we get, and we won't go through its solution. It is still elementary. So in this case, we have two colors, R and B, red and blue. And remember that reds are not matched to each other, but blues can be matched to blues and reds. So let R of t be the probability that the root is red and not matched along an edge of length less than t. And B of t is the same for the blues. So again, as before, the process of available red and blue children of the root form independent inhomogeneous Poisson processes of different rates, R of t and B of t on the line. Now, what is the equation for B of t? So what is the chance that the origin is blue and yet not matched within distance t? So first of all, the chance that the origin is blue is this 1 minus epsilon, and then the expected number of points it would match is given by this integral. So because it can be matched with reds or blues. So And exponential of minus that is the chance that there are no such points that it could be matched to within this interval of t. So we get this identity for B of t. For the reds, we have a similar identity, but because reds can only be matched with blues, the integral here only has B of u inside. And again, we have these two integral equations. We differentiate them to get a pair of coupled differential equations, with their corresponding. So sorry, I switched too far. So these are the differential equations. These are, we know the boundary values. B of 0 is 1 minus epsilon. R of 0 is epsilon, and this pair of equations is not hard to solve. And when we do, we can solve them exactly, and we find that B of t does go to 0 as t goes to infinity. Corresponds to what we know, that the blues will all get matched, but R of t goes to a positive constant that we can compute, and so the conclusion is that with positive probability, the root is red and unmatched. That's true on the PWIT, and then a more precise analysis of the coupling between the PWIT and high-dimensional space gives us that the same holds in high-dimensional space, provided the dimension is high enough with a quantitative element there. So, you know, I wrote out the calculation for the differential equation, but I won't go through it now. So unless there are questions, then in the last 15 minutes, I want to tell you, you know, a different story, still on matching, but two-dimensional matching. So I'm looking if anyone has questions about what I described here. I'm looking at the chat, or you can just unmute yourself and ask.
Why don't you just go ahead, and some questions they will unmute themselves.
Okay, let me go ahead to the
Two-dimensional case.
To something on the two-dimensional case, and okay, so let me go there. So I have to change the share. So the two-dimensional case is work with Nina Holden, who was at MIT at the time. Now she's at NYU, and Alex Jai, who was at Stanford. Again, this is the comparison that you already saw in 2 dimensions between the optimal matching and the stable matching. But here we're going to look at a different process, which is the gravitational allocation and matching. And let me, sorry, I'll go more slowly. Okay, so so this is a picture that we contributed to the notices of the AMS a few years back, and but it's an example of a gravitational allocation which we will use for matching. So what is this? So you see the points, the black points here are centers or stars, and each one will be allocated a piece of the sphere, and all these pieces or territories have the same area, and the way it will happen is using graded descent for gravitational potential. So, and this turns out to do almost as well as the optimal matching, and unlike the greedy matching, it can be analyzed. So, so formally, we have this collection of centers. An allocation rule is a mapping that takes every point in the sphere to one of the centers or stars, and we're interested in a efficient allocation where the distance between a point on the sphere and the star it is allocated to is typically small on average. So here's the method which does it. So it looks more complicated than the greedy matching, but unlike the greedy matching, the distances can be analyzed. So I told you that for greedy matching in 2 dimensions, we can't analyze the exact tails of the matching. We know it's perfect, but we don't know the tails. So here we're working in, so one change from before is we're working in finite volume, and on the boundary of a sphere. We could also do everything on the torus. And so we start with the gravitational potential, which in 2 dimensions will be logarithmic. So this is this u of x, and the force is minus the spherical gradient of this potential. So if you just take the gradient, it will be a vector pointing into the sphere. So we project it on the tangent plane to get the spherical gradient of the potential. And then we apply gradient descent using the gravitational potential. So gravity here is used not as acceleration, but rather as velocity. Sometimes this is called Aristotelian dynamics. So from every point you solve this differential equation, you want the curve where its derivative at every time is the force applied at that time, and the force is the sum of the, so rather the potential is the sum of these potentials from all the points. So the force will be the sum of the gravitational forces applied by all the stars. So we have this x, all the stars act on it, but when it moves according to the total action, again, it moves with the velocity given by this force, it will eventually converge to one of the stars with probability 1. So there's only a measure 0 of exceptions. And what is remarkable about this scheme is that each of the areas you get has, each of the territories has exactly the same area. So the basin of attraction of a point Z is just the set of x's that converge to Z when you apply this dynamics. And so for every point x, C of x is the point that it's mapped to at the end. So it's going to be Z if x is in the basin. And there are a few points thrown to infinity which don't converge to any star, but these we can show they have area 0. Okay, so this is the picture of a small piece of the gravitational potential. So it has value minus infinity at the stars. And you can think of the process by putting a pebble anywhere and seeing where this pebble will roll into. That will tell you the basin of attraction of each of these singularities or stars. So one might wonder, how do you get equal area? This is true for any configuration, not just for a random configuration. So here is an example of points that seem bunched together. So it seems unlikely first that the center here will get the same area as the other points. But when you actually analyze this, you see that it does. So even points from quite far away will, because the other gravitational forces will balance, they will go to the center. And when you calculate the areas, they're all equal. Another surprising case is, suppose you have this isolated point in the South Pole and a lot of points in the North Pole. So it seems like the basin of attraction of this might be bigger than the others, but it's not. And the reason is that these all bunch together and they pull points that are closer to the South Pole up. Now, there is a one-page proof, which I don't have time to go in detail, but it turns out just as a consequence of the divergence theorem, you get that the areas must be equal. And this is a principle that was elucidated, I think, first by Moser around 1990, a principle of transport using Laplacians. So this is kind of a very nice fact, which is said just follows from the divergence theorem. It's okay, when we proved it, it's new in this setting, but it's really not a new principle. It's well understood in a variety of other settings. What was new in our work is the proof that the distance traveled by a point is at most root log n. And here are some pictures based on a program written by Manju Krishnapur of how these allocations look. So this is when we have more and more stars, and you see the shapes get more elongated because we're normalizing to have endpoints on a sphere of volume n, or of area n. So we might expect these areas to have diameter 1, but in fact the diameter grows with the number of points, and so they get more kind of salamander-like as the number of points grow. Many of our techniques originate in work of Nazarov, Sodin, and Volberg in 2007, who analyzed not random points, but zeros of a Gaussian analytic function. I don't have time to go into that. And there was also prior work I did with Chatterjee, Ron Peled, and Romik, which is Annals of Math 2010, about the high dimensional case of this gravitational allocation. I won't go into that. What is the connection to matching? So you can use this gravitational allocation to create a matching algorithm which is very efficient on average, not in terms of its extremes, but on average, and is within constant of the optimal matching. So in 2 dimensions, back in 1984, Atai Komnost and Tusnadi found that, again, if you have 1 point per unit area, they worked in the square or the torus, but their proof works fine on the sphere. If you have 1 point per unit area or of each color, and you do optimal bipartite matching, then the distance traveled will be order root log n with high probability. So again, we're putting it on a sphere of area n. So the diameter of that sphere is root n, because it's a 2-dimensional sphere, and the distance traveled by a typical point in the optimal matching is root log n. And turns out the same happens in the following scheme of gravitational matching. So how does that work? We're going to think of the blue points as stars. So we put them in place, and we're now going to add the red points one by one. So a red point comes in, it sees all these gravitational forces acting on it, and it moves to one of the blue points, not necessarily the closest one, the one where the gravity takes it, and it's matched to that blue point. These two are taken out, and then we repeat. We take A2, we see how the total net force of gravity acts on A2, it will match it to one of these points, and we take them out and repeat. So, and this we can analyze. Why can we analyze this? Well, we can't analyze, say, the greedy matching. The reason is this uniform error result, because after you put in the first point, okay, so the blue points we're going to put uniformly at random. Then we throw in a red point, it's matched to some blue point, and we take it out. Now, what is the chance that before we put in the red point, what is the chance that each of these blues will be captured first? Well, it's just their area of their basin of attraction from the total area. So it's just 1 over n. So it means when I look at these blue points, before I put the first red point, the chance of each blue point to be matched is the same. So if I start with n uniform points, and then after I put A1 and match it, now I have n minus 1 uniform points, because if I take n uniform points, remove 1 at random, I have n minus 1 uniform points. So because the structure is preserved due to this uniformity theorem, we can analyze the iterative process, which is very hard if you were to use Voronoi cells instead of this gravity.
Yuval, you can, yes. Maybe you should close soon.
Yes, we'll finish in 2 minutes. So, so because of this, we can analyze this matching in terms of the analysis of the gravitational potential. And I want to close, so I won't do this analysis, and I want to close with one video showing you one process. So let me one other very natural process, which is natural for physicists, yet we cannot rigorously analyze it, and this is electrostatic matching. So we start with red points and blue points, and now everyone can be, so reds repel the reds, blue repel blues according to electrostatic rules. So and blues attract reds. So I'll run it again. Now, when a blue and a red match in this video, they get green. So while this electrostatic method in finite volume, we can show it creates a perfect matching, we are unable to analyze the distance in the matching. So the theorems that helped us in the gravitational case was the fact that when we had n blues and removed one, we were left with n minus 1 blues that had the uniform distribution. But with the electrostatic case, we don't have any handle when we start blues and reds uniformly. After some time and movement, we don't have any understanding of the distributions. So this is kind of a challenge. Electrostatic matching seems to do very well in practice, but there's no proof about that. So let me end with that. Thanks for your attention.
Well, thank you very much. Let's unmute ourselves and thank Yuval for a very interesting talk. Why don't you stop sharing so open for comments?
Sure. Let me stop sharing. All right.
Yeah. Are there any questions? I was wondering, is it analogous to the gravitational matching in higher dimensions?
Yes, I briefly mentioned it along the way. So it can be done in higher dimensions, both in finite and directly in infinite volume, and it turns out to be easier in some sense to analyze in higher dimensions, in the sense that the average distance of the matching when we put 1 point per unit volume is constant. So again, we didn't try it in this asymmetric case, but for the symmetric case, the higher dimensional, for any fixed d greater or equal 3, you can do it either on the sphere or directly in all of Euclidean space. You get, when there is 1 point per unit volume, you get the average distance traveled is 1, not root log n like we had in 2 dimensions, but average distance is order 1. And there even is exponential tails for the distance traveled. So the process is very well behaved in higher dimensions. And that's this paper from 2010 in the Annals of Math with Romick and Peled and Chatterjee. So the newer work, which is already from 4 or 5 years ago, is in the 2-dimensional case, one cannot do this in infinite volume. The process is not well defined. But in finite volume, say on the sphere, we can do it, yet the average distance goes up with the number of points. That's basically why it doesn't make sense when you have infinite volume and infinite many points. But it goes up slowly. Root log n is still a pretty slowly increasing function. And that's kind of forced by this Hungarian theorem, where they prove that a bipartite matching in 2 dimensions of n points with 1 point per unit volume has to have average distance of root log n.
And are there any sort of direct applications of these matchings?
No.
No, okay.
I should say that in some of the slides I had, so there is in the case of 2 dimensions, there's actually some very precise, beautiful predictions on the behavior of the optimal matching in 2 dimensions for when you work in and you measure it in L2. So you don't measure the average distance, but the average square distance. And there, the physics predictions have recently been verified, and it appears that this gravitational allocation, although it's not, or a version of gravitational matching, not exactly the version I described, but a variant of that is optimal when you look for L2 distance rather than L1.
Mike, you
I have a question.
Yes.
Dr. Perez, you said no necessarily applications, but something struck me. The NIST is, of course, looking at post-quantum crypt, and all of their advanced candidates are all the NP-complete problem of locating closest lattice vector to the origin in high dimension. So the question I have is, like, the first thing I would have thought of for this method would be that it would play some role in testing the difficulty of cryptographic schemes in high D lattice model.
So the issue is that closest vector and the one which it converges to via gravity are not the same, not even in 2 dimensions, and certainly not in higher dimensions. So so it's true that you can much quicker find the force of gravity by multiple methods than you can actually find the closest point. But it doesn't help you with the so it's not like this solves the closest point in high dimensions. The gravity methods do have quick computational approximations, but they're different than the closest distance. That's one thing I was trying to emphasize.
Are there any other questions? If not, let's thank Yuval again for this interesting talk, and see you next week.
Yes.
Yeah. Thanks a lot.
Thanks for the invitation, and thanks everyone for attending.
Thank you. Bye-bye.